So hello all, I'm Isaac. I'm from Canada, but I'm based in Estonia, a little Baltic country. I work at Zendesk, and my team works on ML-powered features that analyzes millions of conversations every day. And in my free time, I help maintain the Massive Text Embedding Benchmark. You might have heard it as MTEB. So just a quick show of hands, how many people has heard of MTEB before? Most of the room, awesome. Okay, so you already know that it's an open source embedding model evaluation framework, and it features a leaderboard that shows each model's performance and ranking on a benchmark. And for creators of new models, they can just run the benchmark and report the results, and this all sounds simple, right? Except not really. Not really. So when we try to verify these results, we sometimes can't. And why is that happening? Right? Before I start questioning my own sanity, I want to check some obvious things, like did I run the correct benchmark? Am I using a different version of the dataset, or the right version of the model? Or has something changed in the code? And we know that MTEB keeps track of a few things that are relevant to all that. For example, for datasets, we pin a specific Hugging Face dataset revision. For models, the checkpoint revisions are also pinned, and the code is versioned on PyPy. And MTEB also keeps track of these revisions in the results file. So we know which specific dataset, which model, and which code version generated these results. So on paper, everything should be reproducible. Except for some reason, it just ain't. So let's find out what the real issue is. So in this talk, I want to dig into why reproducibility in embedding benchmarks is hard, especially in the current dataset and model trends, what we learned from maintaining MTEB in the past year, what actually is working, and what still needs fixing. And so far, we've talked about how making benchmarks reproducible on paper is like, fixing versions and whatnot. But that's only half the problem. The other half really is compute. When we look at reproducing benchmark results that involves big models and big data sets, they require a lot of compute resources, even if everything is technically versioned and correct. And when we look at the leaderboard on the MTEB English benchmark, there's an increasing number of top-ranked models that have 7 billion parameters. And these are not cheap to run, right? So let's take a look at some numbers. One of the embedding model papers from last year reported how long it took to run the full English benchmark on MTEB. Now this is V1 of the English benchmark. And that's almost 2 days non-stop on an AWS P4D instance. I don't know that by heart. I just have to note that down. But any ideas on how much that translates to in dollars? Hundreds of dollars? Raise a hand. No? Thousands of dollars? Yeah, okay. Tens of thousands? Okay. It is around thousands. So when we look at the on-demand pricing, it gives around 1,800. Though if you can shell out around 200K, because one could, to reserve this instance for a year, to run this one model on one benchmark would cost around 1K instead. Right? What a bargain. It's starting to sound like you need a cloud budget just to reproduce benchmark results, let alone doing any model training. And it's not just the models. The datasets are getting bigger as well. And one of the co-authors from the same paper pointed out that the largest dataset from MTEB English was MS Marco, which takes about 7 hours to run on the same instance. And beyond this, critiques on current benchmarks suggest that they're lacking in multilingual data and domain diversity. So to help make benchmarks more realistic and more challenging, we want more languages and more domains that are included in the coverage, which actually means more tasks to be run. And this becomes quite a significant feat to reproduce any large model results on benchmarks that have any large datasets or a large number of datasets or both. And it seems like we're in a bit of a pickle. Like we're stuck in a loop starting from the orange star. And we want to cover domains and more languages, so we include more tasks, but then we don't want to spend too much on compute, so we want to remove some tasks. But then if we don't include enough coverage, then it's not challenging enough. Then people might not use it as much. So how do we get unstuck? And this is exactly something we explored in one of our recent papers, where we were looking to expand MTEB to many more languages in a multilingual benchmark. And a big part of the bottleneck we realized in eval is in inference. So one idea we had was just to run fewer examples. And the key here is to figure out which samples to run on. And thanks to previous literature, there are a few tricks that we could use. For clustering, for example, instead of encoding the entire dataset, we would randomly encode 4%, and then sample 10 sets with replacements, and we do k-means on that. And then we would average the scores and report that instead. And that led to around 16 times end-to-end speedup while preserving model rank. So it sounds pretty good so far. And for something like retrieval, we would randomly select 1K queries instead of using all the queries. And then we would then keep the top 250 documents. Oh, we're good. And that capped the number of documents at 250K. And some reduction we have seen is as much as 20 times. There's nothing more on the slide, so don't worry. For something like by-text mining, where you're given a parallel dataset with a parallel corpus of like one language and the other, we cache the embeddings. And what that means is that some sentences are shared, so you don't need to encode them again. So for example, in Flores, for the English split, instead of encoding 400K sentences, we only encode 1K, another huge saving. And at the same time, we might not want to run every single task, and we can choose to run only those that have the most bang for the buck, so to say. And when we built the multilingual benchmark, we started off with around 500 tasks to cover as many languages as we can. And then we filter away some data sets that have, for example, machine translated data, underspecified licenses, or highly domain-specific things like code retrieval. And that leaves us with around 300, while still covering over 250 languages. And then we run the subset on some models, so like some big ones, some medium ones, and some small ones, and then iteratively remove tasks that are the most predictable. And then we would also avoid removing a task that would remove a language from that task category. And then we ended up with around 130 at the end for the multilingual benchmark. And the same procedure was repeated for the English benchmark. And as a result, the new MTEB English benchmark only uses 2% of the original number of documents while maintaining model rank. And the number of tasks also reduced to 40. So now the runtime for a 7 billion model is around 3 hours on an H100 GPU. So I know that it's not entirely apples to apples, but when I tried to quote another pricing from another GPU provider, that translates to around $10, which is a huge reduction in compute requirements. And for the big model problem, the new multilingual benchmark actually gave us some insights. The key here is to recognize that the world is inherently multilingual. Embedding models that are pre-trained in a more multilingual setting can yield similar performance to, or often outperform, much bigger ones. And what that means is that we see a model that is 12 times smaller than a 7 billion model perform just as well. And this really challenges the assumption that bigger is always better, and show that with the right training setup, smaller models can be highly competitive, especially across multiple languages. And so zooming out a bit, the multilingual benchmark also reveals notable performance gaps in mid-resource languages like German and Polish. You can kind of see the 7 billion model being outperformed by much smaller models, starting from the French line and beyond. And that is in decreasing number of speakers for the languages. So we've now tackled the scale problem. But there's another challenge, and here's a hint that it's subtle, and it could change your results with just a few words. What do you think that contributed to this score difference given the same data and the same model? It's prompts. The second big challenge is related to a specific variant of embedding models that are instruction tuned. And turns out that these models can leverage prompts to boost performance. But the reliance on prompts also mean that if you use a different prompt or it didn't use any prompts, things could go very badly. So even though if you have the same model or data, your results could still vary just because of one missing sentence. And in practice, how these are used could vary by model. Sometimes these could be fixed prefixes, or it could differ by task type. Like, for example, that is for semantic search, or it could differ by a task. And you can see the trend that prompts can quickly become very tailored to the task, like specifying that you're retrieving from Reddit posts, or you're given a web search query. And so we need to keep track of these as well. And luckily, in MTEB, task-specific prompts are stored within the rest of the task metadata. And this is also where you will find stuff like what language this dataset is in, what the main metric is, and so on. And on the model side, some models will use an instruction template, like on the top, where the task-specific prompt can be placed as an instruction. And for the rest of the model-specific prompts, they live with other model metadata, like how big it is, what framework, whether it's open, weights or not. And these are all committed to the repository, so they're version controlled. So does it really work, right? It does. And we often find the missing points because of this. And sometimes the differences can be small or large. But also, often, prompts remain quite a common issue when introducing new models to the repo, even for maintainers. But at least that we're learning these lessons in public so everybody could see the fruits as well. And so just as we're getting a handle on text embeddings, the field is rapidly expanding beyond text. And each of these new modalities bring its own reproducibility challenges and some familiar ones in new disguises. So expanding embedding benchmarks to handle different modalities like image, audio, or mixed multimodal input, it's a natural next step. And as we explore these extensions, we ran into challenges that go beyond just adding datasets. And each input type brings its own quirks, so to say. For image, for example, there's a notion of pre-processing, like cropping and resizing. For text and image, how these modalities are interleaved could be model dependent. So it could be through concatenating the embeddings, learned fusion, or sometimes in VLMs, some sort of token level mixing. And for audio, there's sampling rates and padding to deal with. And all these small details could easily be why results are not matching. And besides inputs, models can easily be a source of variance as well. And we want to load the right model in the right way. So different image and image text embedding models can be loaded in different ways. So like here, for example, you see OpenClip and visualized BGE. They are initialized from different libraries, and we can't just pass the same parameters to the loaders. And the way models call encode or predict can be different as well. One uses encode image, and one uses just vanilla encode. What this means is that these differences add another small layer of complexity to reproducing results. And a third way is related to normalization. We see this in both text and image embedding models, where sometimes the step is explicitly needed, and sometimes it's not. And sometimes we just don't get it right for the maintenance team and need a gentle nudge from the model creators. And also, just like text embedding models, VLMs and image embedding models could be massive. So to deal with the first model implementation problem, we standardized the model interface. And what this means is that all embedding models are now enforced to have the same input and output types and methods, which should help avoid inconsistencies from model to model. So for the image text embedding models, for instance, these are expected to have specific methods to get image embeddings, text embeddings, and the fused interleaved embeddings. And this will also help evaluation smoother. We can plug in new models without having to tweak the code for each task. And on the user's point of view, what this really means is that the only difference in running a model and a task is in the names, the task names and the model names. This, there's nothing that changes, and it really simplifies things. As for the big model problem, we found a very similar trend to while writing the MIEB paper, that smaller models can achieve very similar performance compared to larger ones. And especially, we saw, again, another big difference in model size, but while matching model performance. And this is, again, drawing light to more efficient and more effective training strategies for embedding models, and not just for academic curiosity, but for practical applications that focus on compute and latency as well. So we have identified problems and some solutions. Why should you care, right? What's in it for you and the broader community? The first and foremost is that a lot of the work is done for you. We have done a lot of the building, learning, and it's fully open source. And all you need to do is pip install or UV install or whatever you like. And this hopefully saves you time so that you can focus on other meaningful work like, navigating office politics. To run anything we have seen so far, it's as easy as running a line of code. As long as they are sentence transformers compatible, they could be run without a model implementation. And here's what you would run for the latest Quen embedding model that was released last week. And the community also acknowledges the importance of a unified eval framework that prioritizes reproducibility. Both academic and industry labs use MTEB as their go-to framework. And now we see more prominent benchmarks view MTEB as a longer-term framework for maintenance as well. For example, the visual document retrieval benchmark from the Kopali paper was recently transitioned to MTEB because the core maintainer is finishing his PhD. And of course, major thanks to the current team of maintainers and contributors, which without them, this wouldn't be possible. So I don't want to paint too rosy of a picture here. We know that MTEB has made reproducibility easier and better, but we haven't solved everything. One big topic is that we haven't spent much time on is hardware. Different hardware is likely to introduce some kind of variance, especially there are known issues with stuff like floating point non-determinism in GPU operations. And so maybe it's as easy as adding this one line, but there may be more than meets the eye. So if you have any experience in this, we'd love to chat. I mentioned before that we pin dataset versions, but public datasets aren't static artifacts like we want it to be, especially when we rely on Hugging Face datasets in other people's accounts. So when this happens, it's often outside of control if the dataset is taken down for any sort of reason. And one of our current efforts is to start rehosting datasets that are in the most popular benchmarks under the MTEB organization on Hugging Face. So if you feel like reproducibility is also important for you and your team, check out one of these tagged issues and help make embedding benchmarks better for everyone. Thank you.
Thank you, Isaac. Any questions for Isaac?
Yeah. Thank you for the talk. How straightforward is the interface for redefining a test?
Redefining a test, you mean?
For example, let's say I want to change the instruction that's given to that specific model many times. So essentially, I want to see if I can improve that embedding model by changing the instruction set. Does your API interface quite flexible, or is it going to need some work to do something like that?
I think these are currently specified as like a dictionary passed into the model loader. And so I suppose you can vary that with different keys as you wanted to test them.
Awesome. Thank you.
Thanks. Any other questions?
There's one over on the left. Oh. My left. Sorry, your right.
Yeah, I was wondering, what is the process for new datasets getting integrated into MTEB? Is there any kind of defined process involved, or does someone just throw out a new dataset over? And
Yeah. So on our docs page, we lay out a step-by-step process to how to add a dataset, and that applies to models as well. Ideally, these are hosted somewhere like on Hugging Face, and then that goes through a PR process for you to define an object. For that, we would define what type of task that is, and any relevant metadata, like any citations and more, what domain that is, what language that is. And then from there, one of the core maintainers will look over that, and then it's as easy as just checking that, and then it's in. So when you do MTEB available tasks, you should ideally be able to see what's there as well.
And would there be any process kicked off to re-evaluate all the models based and also on the additional data set, or is that's up to the model maintainers?
Yeah, okay, I see what you mean. So the current process goes as we store the results in a different repository, and these are submitted by other people as well. And if it's on, ideally, we would have a model, we require them to have a model implementation done and a task dataset implemented already. So we're able to just run that command and verify as a spot check fashion whether these match or not. And those results are then stored and not touched really again. But we do write down, what version of the repo we used to produce these results in case we would need to check them again. But yeah, they are just not touched.
Thank you. Yeah.
Thanks for the talk. I wonder how frequently model maintainers are gaming this benchmark. So accidentally training on a test set and all that stuff.
Often. What I didn't put in my talk, which I can now talk about because you asked a question. Haha. There's prepared slides. So we do see that, but we don't see blatant attempts to train on the test set. I think that is just outright cheating. We do see, however, a lot of models training on the train set of the benchmark. So it's not entirely cheating. It's like, okay, this is in that distribution, this is in that domain, and we want to be able to market that as well. And we have something called the zero-shot score that is designed just for that, where we encourage model creators to report what datasets they have used to train. And then we calculate, okay, out of those, how many datasets are within this benchmark. So for Quen, for example, I'm not sponsored. They're just on the top-ish. It says 95%. What does that mean? Is like, if we have 100 datasets in that benchmark, they have used 5 datasets train splits within that to train their model. And we see NVIDIA, for example, they have used quite a lot because their score is in the red. And of course, their results would be quite high when they do that. But at the end of the day, the question here, at least for such a benchmark that is not super domain specific, is how generalizable these models can be. And so what we're really interested in is, a high green score and also a high ranking on the benchmark. Yeah. No, thank you for your question.
Thank you, Isaac. Let's thank our speaker again.